Hey you guys, hope everything is going well today. I want to briefly go through this assignment that we did not go through on Friday. Make sure you've got the correct answers, and I want to explain a few things. So first off, number one, the elements that Mendeleev predicted: gallium, scandium, germanium, and rhenium. Mendelevium, I should say. Atomic number 101 was named after Mendeleev. I'm going to put these up here, and you can take a look at your group numbers and the elements that should be in those groups. But I really want to jump down to the chemical and physical properties that you should have gathered from the video. So, chemical and physical properties for group 1 lose valence electrons very easily. Because there's only one valence electron. The fewer valence electrons on the last occupied energy level, the easier it is for an atom to lose it, which makes it increasingly more violent, or the reaction would be more violent. All the elements in group 1, except for hydrogen, of course, one of their main characteristics is they react violently with water and oxygen. Most of those metals are soft enough to be cut with a knife. They are shiny unless exposed to oxygen. Then they will react with oxygen and get kind of a film on them. But when you cut it in half, you'll see how shiny they actually are. They float in water, so they're less dense than water. They are very reactive. And they produce what you call an alkaline solution in water. So when they are put in water, they produce a basic solution. So basic solutions would be like soaps and cleaning products. If you ever have to clean your bathroom, most of those cleaning products are alkaline solutions or basic solutions. Those are some major chemical and physical properties. And like I mentioned before, those group 1 elements, I've got a few pictures I've drawn here. So those group 1 elements get more violently reactive as you go down the group, and that's because that valence electron is getting further and further away from the nucleus. And when that valence electron gets further away from the nucleus, there's less of that Coulombic attraction between the protons and the valence electrons. So it's very easy for another atom to take that valence electron away when it's further and further away from the nucleus, because you don't have a very strong Coulombic attraction. That's the reason for that trend, getting increasingly more reactive going down the trend, or going down the group. Group 2, they're definitely more dense than group 1. They'll actually sink in water. They are still very reactive. They react with oxygen quite readily. They're very combustible. You guys saw that when you burn the magnesium in the chemical and physical changes lab that we did in chapter 1. So it very easily reacted with oxygen. So group 2 elements are very combustible. They're soft as well, not nearly as soft as group 1 elements, but they are soft. These guys react with steam, not necessarily water, but with steam. And, like I said, they're more dense than water. Transition metals, of course, I didn't put the elemental symbols because that would be a lot of writing, and their valence electrons change on a very regular basis. These guys have much higher melting points than your group 1 and your group 2 elements. Low chemical reactivity. They're still going to oxidize or combine with oxygen in the air, but not violently like your group 1 and 2 elements are. They produce compounds that are very colorful, and they do not react with water and oxygen violently. Especially, they do react with oxygen, but you're not going to get this violent reaction and this explosion from it. You're going to get more like a film or a rust, some sort of new product, but it's not going to be a violent reaction. So these guys are definitely less reactive than group 1 and 2. Halogens, halogens are obviously going to be your non-metals, and these guys are reactive in their own right, but they're not reactive that they want to get rid of valence electrons. They are reactive that they want to hold on to their valence electrons. Fluorine is actually the very most reactive non-metal on the periodic table. It is going to hold on to those 7 valence electrons extremely tightly because they are found on that second energy level, and there's a very strong attraction between the nucleus and those 7 valence electrons. So fluorine is going to be what we call very electronegative. It will want to gain valence electrons desperately to fill that last spot to have 8 electrons in the last energy level. It is considered to be very reactive, the most reactive nonmetal in the periodic table. Their states of matter, you guys already figured this one out from the periodic table puzzle. You've got all states of matter, solids, liquids, and gases. Your gases are chlorine and fluorine. Bromine is the only nonmetal that's liquid at room temperature, and iodine and acetane are your solids. Excuse me. They react with metals to form halides, or sometimes they call them salts. Your noble gases, group 18. Of course, they're all stable with 8 except for helium, which is stable with 2. You guys know this from the puzzle you guys did. Very unreactive, though there are several, especially xenon, that form compounds. They just don't do it that often. Actually, honestly, I think xenon might be one of the only ones that actually makes compounds. They're all colorless, monotonic. They don't automatically bond with other elements. Like, for instance, over here at the halogens, fluorine, chlorine, bromine, iodine, nitrogen. Several elements are what we call diatomic. Like, they're never going to be found all by themselves in nature. They'll either be found in a chemical compound bonded to something else, or they'll bond to one of their own. So a lot of times you'll see like chlorine written like this, or you might find bromine written like that. And that's because several of these elements, and not just the halogens, but like I said, nitrogen, oxygen, hydrogen, several of these nonmetals are always going to be bound to one of their own if they're not found in a compound. Versus our noble gases are going to be found alone by themselves. They're not going to necessarily combine with another noble gas or a noble gas of its own. Their boiling point does go down, boiling point increases as you go down a group. That's one of the trends. Okay, let's flip over to the back side, and let me talk about a few of these, and I'll explain a few of them. I already talked about the alkali metal reactivity increases. Density, it's going to increase. So what's going to happen is you're going to have these bigger atoms, and they're going to have more stuff in it. So you're going to have more mass per unit volume. So as you go down a group, the atoms get bigger. You got more protons, more neutrons, hence more matter per unit volume. So the density is going to increase. When it comes to melting boiling points, it actually decreases. So when you're talking about metals, they're only, other than being bound to another non-metal. Okay, if we're talking about a chunk of metal, they're going to be the same atoms bonded to one another. It's never going to be like sodium that's bonded to potassium, or magnesium bonded to potassium. You're never going to have two metals that are actually bonded together. To have like a chunk of sodium, you would have to have a whole bunch of sodium atoms bonded together. And so what happens is this: if I have a chunk of sodium, or actually, if, let's say, go down the group, if I have a chunk of rubidium, okay, the radii gets much larger, of course, as you go down a group. And the attraction, I'm going to show you right here. Okay, so the attraction between two metallic atoms of the same kind. So if you have a large radius, the attraction between your valence electrons and the nucleus of the other atom, okay, as that gets longer, your melting and boiling points get lower because there's less of attraction between atoms. Like lithium is going to have a higher boiling point or melting point than rubidium because each of the lithium atoms has a much smaller radii. And so the attraction between the nucleus of this lithium atom and the valence electrons of this lithium atom is going to be stronger because you have fewer energy levels to get through for this positive charge to reach the valence electrons. So if you have a larger radius, the strength of attraction between the positive here and the negative here is going to be less than with atoms that have smaller radii. So that's the reason for that trend. So both of these on your alkaline metals and your alkaline earth metals are going to decrease for that reason. Alkaline earth metals, same thing. Reactivity increases as you go down a group. Same reason. These guys just aren't nearly as reactive as your alkaline metals because they have two valence electrons. So the more valence electrons you get in that last energy, the less reactive the atoms actually are. Density, same reason as before. The more stuff you have per unit volume, the denser the substance is going to be. And then melting and boiling point decreases, just like I told you before, because the increase in atomic radii. Okay, let's move over here to our halogens. Halogens reactivity decreases as you go down a group. So what happens is electrons, or I should say the atoms, are less willing to accept electrons, or they don't have nearly as strong of a pull on electrons from another atom, so it makes them less reactive. So the stronger the pull they have for valence electrons to another atom, the more reactive they're going to be. So as you go down a group, okay, that want or that attraction from the nucleus, kind of like I said before, the valence electron of another atom, that pull or that attraction is going to decrease. So that's going to decrease their reactivity. Density is going to increase, same reasons as before. And if you kind of think about it, they are going from gases to solids, and solids are definitely more dense than gases. So as you go down a group, you're going to go gases, liquids to solids. So their density is going to increase. Melting and boiling points for both actually noble gases and for the halogens, they're going to increase. Their melting and boiling points are going to increase, and I'll try to explain to you guys why. So, see, there's a blank sheet of paper here. Okay, so let me go ahead and explain to you why we have this trend of boiling point and melting point that are increasing in your halogens as you go down a group, your group trend. As you go down a group in your halogens and your noble gases. So first of all, there's something called, and once we get to bonding, we'll talk more about this, but it's called van der Waals Forces. Okay, so van der Waals forces. So these forces happen between they're very spontaneous forces that occur spontaneously between the atoms of noble gases and halogens. So for instance, if I was talking about 2 argon atoms. Okay, so remember, as you go down a group, you're going to increase in the number of electrons in the electron cloud. So in argon, in our electron cloud, let me start over. Okay, so these are our nuclei, and let's say this is my argon atom, and this is my other argon atom. So what happens is this. Those electrons move around very randomly and very spontaneously. And if our electrons in my argon atom happen, okay, start over, happen to all be on one side of the electron cloud. So if I've got my electrons that are randomly, okay, moving, and they've just happened to kind of accumulate on one side of the electron cloud, okay, it is going to cause an attraction, okay. So this bulk of these electrons that happen to just pile up on one side of the electron cloud is going to have an attraction to the nucleus of the other atom. And it's a very spontaneous attraction, and it only occurs when those electrons happen to accumulate on one side of the electron cloud. They're called van der Waals forces, and they're actually fairly strong forces, believe it or not. But this causes the atoms to be attracted to one another, when actually your noble gases wouldn't really be that attracted to one another. And this happens in the halogens too. So if you have this conglomeration or this accumulation of negative charges, okay, it is going to be attracted to the positive charges in the other atom. And that attraction is fairly tight, or it's a strong attraction. So what happens is when this attraction is larger, okay, it's going to cause your boiling point and melting points to go up, because it's going to be harder to break these forces to get that state of matter to change, to go from a solid to a liquid to a gas, or to go from, a solid liquid to a gas, whatever it may be. So that's why that trend exists. As you go down a group, the atoms have more electrons, and if you have a huge conglomeration of electrons on one side, it increases the attraction to the nucleus of the other atom, and these are called, like I said, van der Waals forces, and it's hard to break that bond, making the melting and boiling points a lot higher as you go down a group. We'll talk about those more when we get to chapter 6. Okay, so going on, noble gases, they're inert. Trend for density goes down or increases, just like all of the others. More matter per unit volume, more density. We talked about increases in boiling points, some real life applications. There's a ton of them they mentioned. Fill balloons, light bulbs. Radon is used in radiotherapy or radiation for cancer. Xenon is a natural aesthetic. Krypton and xenon are used in lasers, and xenon can be used in car headlights. And I think I covered most of those. I may have missed one or two. Okay, so that will consider your assignment to be graded, and on the top of your homework assignment, you should draw on the top side. I'm going to have you draw a daisy. Like that. See how pretty that is? Oh, and then make a sun to go along with it. Okay, you guys. I will see you guys tomorrow. Take care.